uh, our Toronto Center, just to let you know what we're doing. As you can see on the slide, we thank the CMOS member for their support and hope that you continue to renew your membership annually. So if you're not a member, there's the website at the bottom, URL, and also the scan. Just also wanted to show you that in addition to the webinar, we also have Science Fair Awards that we offer to the Southern Ontario elementary and high school students. So these are some of the activities that we do. Just also like to remind you that next month's seminar will be given by David Sill from the Western University about some of the work that they're doing on extreme weather. And I think they started a new program on severe weather lab. So that would be interesting to see. That's it's on the 18th, I believe. Announcement will be coming out soon. So that's something to look forward to next month. So now I'll introduce today's speaker. Today's speaker is Neil Tandon. He's the Associate Professor of Atmospheric Science at York University in Toronto. In 2013, Neil obtained his PhD in Applied Physics and Applied Mathematics from Columbia University. His research focuses on climate dynamics. He uses a combination of models, observation, and mathematical analysis to investigate how motions in Earth, atmosphere, and ocean influence climate. His work has helped to clarify the physical processes driving long-term changes in the atmospheric circulation with implication for desertification, cloud abundance, extreme precipitation, and Arctic sea ice. He also investigates variability in ocean circulation and its relationship to other aspects of climate variability. So the title today is Building Confidence in Regional Projections of Extreme Precipitation. Over to you, Neil.
All right, thank you very much, Amir, and thank you very much for the invitation to speak here. And it's nice to hear that David will be giving the next one of these, so it'll probably be some nice complementary perspectives of extreme weather. And I'm coming at this from the climate perspective of trying to understand the long-term behavior of these sorts of storms and how climate is influencing the long-term characteristics of how often these sorts of storms occur and how they behave when they do occur. So one of the, many of us in our whatever region we're in, we have likely experienced some sort of extreme weather during our lifetime. And in Canada, one of the big examples that we look back to is the 2013 Alberta floods, which at the time was the costliest disaster in Canadian history. It ended up being outdone by the Fort McMurray fires. And when you look at the amount of precipitation that occurred in that region, it was about 200 millimeters of rain over a period of 48 hours. This was considered a once in 50-year event. And in absolute terms, if you talk about this amount of precipitation, you could go to other regions. Like I was in India over the summer, where during monsoon, 200 millimeters of rain is actually not that extraordinary. So for particular regions that are not well equipped to handle this amount of rain, it can be quite devastating. And in Toronto, just this past summer, we saw an event that was about 100 millimeters of rain, and that was enough to flood the Don Valley Parkway, Union Station. So this example helps us bring up certain terminology that will come up repeatedly when you're talking about extreme precipitation. First of all, there's the terminology of intensity, extreme precipitation intensity, EPI, which I'll use repeatedly, which is the amount of precipitation during a particular extreme event. So in this case, 200 millimeters of rain was the intensity. And then with extreme events, you can talk about the duration. So in this case, the relevant duration was about 48 hours. And then another thing that comes up, another term that often comes up is the return period. How often do these sorts of storms occur? And in this case, it was a once in 50-year event. Okay. So what are the observations telling us? You often see headlines pop up in the news about, is this particular event something we expect due to climate change? And when we've looked at the long-term statistics of extreme events, we are seeing some indication of trends. So this is one of numerous analyses I could have pointed to from actual station measurements aggregated over latitude bands, this study in 2013. And the dashed line is indicating the trend in the intensity of these annual maximum events, okay, aggregated in these latitude bands. And we typically normalize it as a sensitivity. So this ends up being a percent change in the intensity per degree of warming, if you look at the label on the left-hand side. Okay, so this just helps to take out any effect of if there's more warming in particular regions and help to just zero in on the particular sensitivity. Okay, and what we're seeing from these sorts of analyses is that there is a positive trend over most of the globe. Okay, and the shading here is giving an indication of the noise level. So anything above this shading would indicate a statistically significant trend, and we're seeing significant trends over most of the northern hemisphere, parts of the southern hemisphere, and the tropics as well. Okay, and if you look at the precise percent per degree of warming of this intensity, if you were to eyeball a global average, you would see something in between 5 to 10% per Kelvin. And this is in line with what we expect from thermodynamic principles. So the more mathematically inclined of you could look over to this equation at the right, but I don't want you to be intimidated by any mathematics here. If you were to look at the dominant term during extreme events that is driving precipitation, it would be the vertical transport of moisture. And so mathematically, that's encapsulated here with omega E, which is the pressure velocity in the vertical direction. And dq star dp would indicate the vertical gradient of the saturation mixing ratio. Okay, so during extreme events, when you have ascending motion, it's typically saturated ascent. And so a term like this would capture most of what's contributing to the precipitation. Okay, and the curly brackets here are just indicating a mass-weighted vertical average. And so if you were to imagine what's happening under climate change, one of the key influences is the influence of temperature on the saturation mixing ratio, the influence of temperature on Q star, which follows the well-known Clausius-Clapeyron relationship. And if you look at the slope around present-day temperatures, that slope is approximately 6.5 to 7% Kelvin. Okay, and when we look at the global average, we see values that are in line with what we expect from that thermodynamic influence. But of course, with climate change, we're not just interested in what's happening globally. We're interested in what's happening in particular regions, and that's where this omega E term, this pressure velocity term, plays a really, really strong influence. And you can see indications of that already in the tropics, right? Where there's a much stronger change than just what we expect from thermodynamic principles. And then conversely, in the subtropics, we're actually seeing regions where there's a decrease in the extreme precipitation intensity projections. Okay, and that's due to weakening of this vertical velocity during extreme events. So regionally, what the vertical velocity is doing has a huge impact on the changes in extreme precipitation intensity. And so much of my talk is going to focus on understanding those changes in vertical velocity, because that's the relatively poorly understood part of this problem. Okay, and that's a challenging thing to investigate because we actually don't have a lot of good observations of vertical velocity. Even in situations where you're looking at station measurements, those are typically giving measurements of horizontal velocity. And if you're going to attempt a calculation of vertical velocity, then you really need good spatial structure to use the continuity equation and then compute the vertical velocity. So that's really challenging to do directly from observations. There's some localized observations around arm sites, like in Oklahoma, where you can get vertical velocity, but those time series are typically around 10 years. And again, very localized. So we're very reliant on models to give us an initial sense of what to expect regarding changes in vertical velocity. And more generally, when assessing the mechanisms of vertical velocity, we're often turning to models to do some initial testing of hypotheses. And then to the extent that we can, we look back to the real world to check consistency and do some sanity checks. Okay, so that will be the sort of approach that we take in this presentation as well. Okay, so the key question that I'll address in this talk, right? There are many possible features of extreme precipitation that you could focus on. Okay, but it fits into the general question of, well, how well are climate models reproducing the observed features of extreme precipitation to the extent that we can do such comparison? And we will focus on, like I said, there are many possible features we can focus on, but we'll focus on the extreme precipitation intensity, EPI, and the spatial scale of extreme events, because we have some recent studies there that I think are illuminating. And then, having done some of that comparison, we will look to the future and assess what the models are telling us about the future changes regionally in extreme precipitation intensity, which again reduces to a question of what the vertical velocity is expected to do. Okay, so as to that first question, how well do models do? There's been some nice comparison done in recent studies to compare global climate models, GCMs, to available observations. And this is one such study from Stefan Fahl back in 2017 in Nature Climate Change, where he compared output from CMIP5 models. So you might know these intercomparisons that are done in line with the IPCC reports. This was done in the 5th phase of that intercomparison, CMIP5. And they compared the annual maximum of daily precipitation from the historical period 1981 to 2000 from the CMIP5 models, and then compared it against one of the commonly used observational estimates, which is GPCP. Okay, and there is some difference of period that's used, but this comparison is typically not sensitive to that precise choice of the time period. And what you notice is that if you were to just focus on the land regions, things compare quite nicely between the models and the observations. There's some pockets, say, over India, where the observations are indicating slightly larger extreme precipitation compared to the models. And you see some possibly negative biases over parts of South America and East Asia as well. But qualitatively, the structure compares quite well, aside from these biases. Okay, and then if you compare over the ocean regions, there's a broader indication that the models are producing more precipitation than what the observational estimates suggest. But then, of course, there's the caveat that the observational estimates are very poorly constrained over ocean regions. We don't have a lot of ground measurements to constrain the observations, and there are uncertainties related to satellite-based estimates of precipitation. And you can see right here, there's this line at GPCP where the satellites cut off. And so there are these issues when it comes to attempting precipitation estimates from satellite observations. So all we can say at this point is that there's a difference between the models and observational estimates over the ocean, but it's unclear if that necessarily means there's a bias in the models over those regions. So far, I would say this comparison is encouraging. Now, when you turn to the issue of the spatial scale of the storms, then there's some more concerning things that arise. So here I am showing results from a study that actually was recently accepted in JGR. And what we're plotting here on the horizontal axis is horizontal resolution of models in CMIP, and this is one of the intercomparisons done under CMIP6, which is the more recent phase of CMIP, including a number of models that participated that were considered high resolution models. So getting down to 25-kilometer models globally. Okay, so that's a pretty recent thing that global climate models have been able to get down to such fine resolutions. And so we included those models in this analysis as well. So again, we're plotting horizontal resolution on the x-axis in the southern hemisphere mid-latitudes. And on the vertical axis, we are plotting a measure of the horizontal scale of extreme precipitation events in these models. Okay, and we're focusing on the annual maximum of extreme precipitation. Again, a lot of our analysis isn't going to be sensitive to the precise choice of return period, but that's the commonly used return period when analyzing climate models over the historical period. And if you were to look at a simulated extreme precipitation event in the southern hemisphere mid-latitudes, it would look something like what we see in the panel in the bottom right. Okay, it actually has a slantwise structure to it, and so you could argue about different ways of measuring this horizontal structure. But to just facilitate comparison with earlier studies, and the way they typically do this is to have a measure of the zonal scale and the meridional scale, and then they combine those two scales in some way. And when you're doing mathematical analysis of physical equations, the typical measure of these horizontal scales is in terms of a wave number. And if you want it in terms of meters, you would invert that and use the inverse wave number. And that effectively is what we're doing with this horizontal scale on the vertical axis, is that we're combining those inverse wave numbers with a sum of squares and then taking an inverse square root. And you end up with something that is back in the units of kilometers. Okay, so if you do this comparison versus resolution, you might have already noticed in this figure that there's an indication of a quite strong correlation with resolution, that as you get to finer resolutions, the spatial scale of these storms is going down. Now, that is something that is concerning because, especially in a region like the Southern Hemisphere mid-latitudes, it's mostly an ocean-covered region, right? Topographic influences are not significant there. You should be seeing that the horizontal scale is dictated by physical processes, things like your Rossby radius of deformation and so forth. They should not be dictated so heavily just by the resolution of the model. Okay, so that is a concerning thing here. Another thing that pops out of this analysis is some comparison with observational data sets. I've included 3 observational estimates here from GPCP, iMerge, and CMOS. Again, these are commonly used observational estimates, and to some extent they're interdependent with each other, relying on similar satellite systems. And if you look at that comparison, the highest resolution models are not necessarily showing the best agreement with those observational data sets. It's something, maybe the mid-high resolution are showing some spatial scales that are within the observational range of estimates. Okay, so getting higher resolution in these models, as long as it's still, all of these models are still parameterizing convection. And so what I think this indicates is that as long as the model is parameterizing convection, it doesn't necessarily give you superior agreement with observations to have higher resolution. You only really see the upshot of higher resolution when you start to be able to explicitly resolve convection. And I'll show some other results that I think will reiterate and provide further support for that point. Okay. So this analysis included all of the models in CMIP6 and high-res MIP. But if you were to focus on particular models in this ensemble, there were some modeling centers that performed simulations with the same model, but just at different resolution. And you can see that with CESM2, there was a 2-degree variant of that model, as well as its standard 1-degree variant, which is shown in the bottom right here. And if you just look at those particular models, what you see would be purely just the effect of horizontal resolution. And you see that with those particular models, under such comparison, you see a drop in the horizontal scale with higher resolution. And then if you looked at the NPI model, again, comparing a low resolution to a higher resolution version of that model, you also see this drop in the horizontal scale. Okay, so it's not just apparent across the entire model ensemble, but there's also this indication from particular models that there's this sensitivity to resolution. Of course, we're not saying that resolution dictates everything. There are, of course, going to be other contributing factors. You see quite a bit of scatter, doesn't fall along a perfect line. Of course, there are going to be other physical choices in the model that affect these spatial scales, but we definitely see an indication of resolution dependence in these simulations. Okay, so why is there this resolution dependence? Why is there this resolution dependence? So to get at that a bit, we've done some additional analysis, and here we're showing on the vertical scale, the horizontal scale of precipitation, extreme precipitation events, if you just looked at the resolved precipitation. Okay, so when you have these models, these GCMs, they have multiple ways by which they are generating precipitation. One of the ways they're generating precipitation is just they ask the question, is a grid box saturated? And if a grid box is saturated, then there's a scheme that kicks in, which is often called a stratiform scheme, which relaxes and produces precipitation and allows moisture to condense to bring that grid box back to below saturation or below saturation. Okay. There is also a scheme within these models that is a convective scheme, which asks the question, is the vertical temperature profile unstable? And if it is, then a scheme kicks in which attempts to simulate the effects of convective plumes, generating vertical transport and producing precipitation. So there's these multiple ways by which precipitation is produced in these models. And we just asked the question, well, what is the spatial scale if we just looked at the resolved precipitation from that so-called stratiform scheme? And if you compare that against the horizontal scale from the total precipitation, it falls very close to this one-to-one line. You would not see this correspondence if you looked at the spatial scale from the convective or parameterized precipitation. So this is indicating that the spatial scales of extreme precipitation events from these models is almost entirely dictated by resolved precipitation. And thus, it shouldn't be surprising then that there's this resolution dependence, because of course your resolved grid scale precipitation, it could very well be sensitive to the grid resolution. Okay, so there's questionable realism with that. In extreme precipitation events, you typically expect to see, especially in models that are parameterizing convection, you would expect to see more of an influence of the parameterized precipitation. And when you look at the actual intensity, which I have an extra slide for if you want to dig into that, the intensity of these extreme events is almost entirely dictated by resolved precipitation as well. So that's questionably, the realism of that is questionable when it comes to these models. Okay. Now, the fact that the precipitation is almost entirely resolved then raises the question, well, why is it almost entirely resolved? Does that indicate that the resolution dependence is due to resolution dependence in the large-scale circulation, which is generating these extreme precipitation events? And we can assess that by looking at the horizontal scale of geopotential anomalies during the extreme events, and that's plotted on the y-axis here, and then plotted on the horizontal axis is resolution again of the models. And we do not see a strong resolution dependence in the large-scale circulation anomalies. So that is an encouraging result here, because it would indeed be troubling if the large-scale circulation was resolution dependent. So what we think the resolution dependence is more likely due to is some combination of poorly resolved fronts or grid scale convection. There's been some earlier studies, such as from the Harrington and Reed study that some of you might be familiar with, that have looked at the effects of resolution on annual mean precipitation and have shown some indication that buoyancy disturbances tend to occur on the finest scale available in the model, and that might be some indication of why there's this resolution dependence. Okay. So despite these concerns about the spatial scale of extreme precipitation events, we will nonetheless push ahead with investigating the mechanisms driving the projected changes in the extreme precipitation in these models, because again, it will help to provide a starting point for understanding the mechanisms that might be acting in the real world. Okay. Oh, another point that occurs to me that I could mention, right? This sensitivity, what you're seeing here is that for a factor of 7 change in resolution, you're getting about a factor of 2 drop in the horizontal scale. If you were to look in the tropics, which we've done in the paper, and I haven't shown here, you would see about a factor of 5 change in the horizontal scale. Okay, so the sensitivity to resolution is actually much higher in the tropics than it is in the mid-latitudes. Okay. So we're going to look a bit at what the models are saying about the future projections in extreme precipitation. This is a study that I led back in 2018, where I was looking specifically at output from the large ensemble of the Canadian Earth System model, version 2. And we were calculating 10-year maxima of extreme precipitation intensity, okay, over that 50-member ensemble. And then we calculated that over the historical period, 1981 to 2000. We composited those intensities of extreme precipitation events. So at each grid point, right, a 20-year period, 10-year maximum, right, there would be two events per ensemble member. This was a 50-member ensemble member. So at each grid point, we had a sampling size of 100, okay, in both the historical and the future period. And we took the difference between those composites and normalized by the temperature change, in this case, the zonal mean temperature change, and you end up with a percent per Kelvin change in extreme precipitation under the specifically RCP 8.5 scenario. Okay. And again, if you were to eyeball a global average of these changes, you would see something around this light blue shading mark, which again is in line with what we'd expect from the Clausius-Clapeyron effect, which would be around 7% per Kelvin. But then in particular regions, you see quite a bit of interesting deviation from that. Okay, for example, much of the tropics, like tropical Africa, maritime continent, tropical Pacific, you see increases that are much greater than what you would expect from Clausius-Clapeyron, getting up to 20% per Kelvin changes. Okay, and then you see, interestingly, regions where there's a projected decrease in extreme precipitation intensity. Okay, so from the observations, there was some indication of this, but with not really rising to the level of statistical significance. But from models, we can see statistically significant projected decreases in extreme precipitation intensity that are mostly confined to the subtropics, such as the subtropical East Pacific, East Atlantic, and Southeast Pacific, Southeast Atlantic. Okay, and as well in the Indian Ocean and over Brazil. Okay. And a number of these features are common to all models that have been analyzed. So there's been previous analysis of CMOS, and the common features are the ones in the subtropical Atlantic, okay, and the subtropical South Atlantic as well. And also subtropical Pacific. Some of the features that are not common to all the models are ones like this feature over Brazil, okay, and northern South America. So much of our starting point or much of our motivation is then going to be analyzing these subtropical regions. And if you were to dig deeper and look at what the vertical velocity is doing in these regions, okay, that would be this plot that I'm showing on the bottom here. And anywhere where there's orange-red shading, it would be an indication of weakening vertical velocity. Anywhere where there's blue shading to dark blue shading, there would be indication of strengthening vertical velocity. All right. And you can see this correspondence in the regions where there's projected weakening of extreme precipitation intensity. There is this projected weakening of vertical velocity. And you can do an even more rigorous analysis where you just looked at the vertical velocity contribution to the vertical moisture transport, like decompose that omega dQdP term. And then you would see a very precise correspondence between the changes in the dynamical contribution to vertical moisture transport and the projected decreases in extreme precipitation intensity. Okay, so hence, that's why that's going to motivate much of the rest of our talk is what is driving these decreases in omega E. And so it might seem a little academic that we're going to focus on these subtropical ocean regions. But the idea there is that long term, we want to understand the dynamical effects everywhere. But our best bet for understanding where the mechanisms driving these dynamical effects, we think, is to start where those dynamical effects are the strongest. And so we're going to start with analyzing these dynamical effects in the subtropical Atlantic, which are the strongest dynamical effects we see globally and are also common to all the latest generation of climate models. And then once we have a grip on what's driving those mechanisms, then we will hopefully at some point turn our attention to land regions where the dynamical effects can be more subtle. Okay. Unless you think this is purely academic, just focusing on subtropical oceans, if you were to look at the summer season and assess the annual summer maximum of extreme precipitation intensity, you would get a figure that looks like this from Canny SM2. Okay, and this shows that dynamical effects during the summer season can extend well into the extratropics. And from CANESM2, we see projections of decreasing extreme precipitation intensity over much of Europe and much of North America. There is reason to be skeptical of those projections, granted, but nonetheless, it is worth pushing ahead to understand why are the models actually projecting these decreases. Okay, and again, it comes down to a question of what is driving these decreases in omega E, which is the pressure velocity. Okay, so one thing to emphasize before we push further with that analysis is that this omega E is a grid scale vertical velocity. These are not convective updrafts, right? So we're not going to be looking at the updrafts due to convection. We're going to be looking at the resolved vertical velocity in these models. So that is a hydrostatic quantity, okay, for those of you familiar with that term. Okay, these are not buoyancy driven vertical velocities, okay, or they shouldn't be, right? There's a question as to whether there is some buoyancy occurring at the grid scale in the models, but and so so when you attempt to analyze the vertical velocity at these hydrostatic scales, you can't just rely on the vertical momentum equation. There is no omega in the vertical momentum equation when you look at hydrostatic scales. You have to combine hydrostatic balance with the thermodynamic equations and the other momentum equations, and that gives you a relationship called the quasi-geostrophic omega equation, which I'm showing here. Okay, those of you who have gone through meteorology programs, I know Gary Clausen here at York brings this up in his dynamics course as well, so this would be something that you've seen before. Me going through a climate program, I actually didn't see this equation for the first time until I was a postdoc. So it's worth doing a quick refresh on some of the key terms that pop out of this equation. And the first thing you typically do to demystify this equation, at least I do this, is to rename some of the terms to make them a little less intimidating. So first, I like to replace the minus u dot grads with ADV to indicate that those are just indicating advection. Okay, so you have a term relating to advection or differential vorticity advection. You're the first term on the right side. Then you have a term related to heat advection. All right. And then to further demystify this equation, you could recognize that the del squareds here are just a measure of curvature. Okay, and for a typical anomaly of a quantity, the curvature is going to have a sign that's opposite to the sign of the anomaly itself. So if you were to look at a cartoon of an anomaly of diabatic heating, okay, a positive anomaly would look something like this, and clearly that has a negative curvature, right? Or a frowning face, if you like to think back to terminology that might have been used in your calculus courses, okay? And then that helps us get some intuition and test our intuition about this equation, right? Because this operator on the left-hand side next to the omega is just a 3D curvature. So that same logic applies where the sign of the anomaly would be opposite to the sign of the curvature itself, okay? And so if you were to block out everything on the right-hand side and just ask the question, what would a positive anomaly of diabatic heating do? Well, a positive anomaly, all these coefficients in front of that term in the northern hemisphere will be positive, okay? And for a positive anomaly, del squared Q would be negative. And then you have a negative sign in front of that, so that would make all of that positive, all right? And then looking to the left-hand side, that would make everything on the left-hand side positive, if that's the only forcing. But if that's all positive, then omega itself has to be negative, okay? And negative omega would indicate that the air is going towards lower pressures, which would mean ascending motion with pressure velocity, okay? And you could follow that through with each term on the right-hand side, one by one, to test your intuition about this equation. And you would find that positive heat advection would go along with rising motion. And then one of the interesting ones that's actually that can be somewhat tricky to interpret is this first term on the right-hand side, differential vorticity advection, which I'll spend a minute on because we have done some simulations indicating that this term ends up being especially important. Okay, so you could hand-wavily think of differential vorticity advection as just capturing the fact that when you have a low pressure anomaly, it tends to go along with vertical motion. right? So low pressure anomaly would go along with a low anomaly in geopotential height, and a low would go along with cyclonic vorticity. If you're dealing with the the typical geostrophic assumption would capture that as well. Geostrophic vorticity just goes like the curvature of geopotential height. Okay, but it's actually a bit more subtle than that, and it's helpful to look at some visuals related to that. Okay, so if you had differential cyclonic vorticity advection, what that's actually saying is that the vorticity is over time getting more cyclonic at higher altitudes compared to lower altitudes. And when that is happening, what is happening is that your layers are getting thinner. Okay, and if your layers are getting thinner, then there would have to be a cooling that occurs in order to maintain balance. And in order, and hydrostatic balance dictates that, right? According to hydrostatic balance, a thinner layer would have to get cooler, okay? And then to maintain balance, then that cooling would have to be balanced by adiabatic cooling, which would go along with rising motion if you dig into the thermodynamic equation. Okay, so that's the more rigorous way of connecting all these things together, right? And if you wanted to assess that mathematically, right, differential cyclonic vorticity advection would indicate that as you go toward higher pressure, going toward the surface, the cyclonic vorticity would decrease. Okay, so DDP of the advection of cyclonic vorticity would be negative. Okay, and then the negative sign in front of that would make things positive in the northern hemisphere. And then you would get, if that were the only forcing acting, then the entire left-hand side would have to be positive, which would indicate ascending motion, negative omega. Okay, so mathematically and intuitively, those things all go together. So to encapsulate that again, in short, what we're saying here is that anomalously thinner layers would indicate stronger ascent. All right, so remember that, because we're going to bring that back. And over the years, what's further helped with analyzing and understanding how the QG omega equation can illuminate extreme precipitation events is to focus on wave-like disturbances. And if you focus on wave-like disturbances, then you can replace this del squared with a -1 over a characteristic length scale squared. Okay, and if you do that, then you get this form of the equation shown here, right? And there's been some research indicating that, and I participated in quite a bit of that research as well, indicating that as the atmosphere warms, you would expect the length scale to go up, right? Because if the length scale goes like the Rossby radius, there's some well-known relations related to the stability increasing and the effect that that would have on the length scale. And so I've argued in the past that the length scale, based on some analysis I've done, plays a key role in weakening extreme ascent with warming. Okay, but other studies have come along that have challenged that finding and have argued for other processes related to dry dynamics or to spatial shifts of things like the Hadley circulation or just a direct influence of changes in vertical stability. So one of the reasons why these earlier studies seem to be coming to different conclusions is that we're all relying on things that are somewhat interconnected. And furthermore, we're all relying on output of models and just performing a lot of analysis of model output rather than doing controlled experiments to see if we just changed one thing, what is the result that we get. So that might have motivated us to really do some controlled model experiments where we could change things systematically and assess the results. Okay. And again, the question we're after is what is driving these decreases in vertical motion in the subtropical Atlantic, right? With the long-term goal of understanding in other regions the changes in vertical motion. So some of you might have already been glomming onto this, the fact that I'm talking about QG, but then we're going to talk about vertical motion changes in the subtropics, and you might say, well, quasi-geostrophy, that's really something that we should only be talking about in the extratropics. I'm not sure we should really be using that in the subtropics, but there's been some interesting analysis done recently where they've looked at the vertical velocity you get from inverting the QG omega equation and compared that to the total velocity. And they find that when you look in the subtropics, you get pretty good matching between the QG omega vertical velocity and the total omega. Okay, so it does seem like this QG omega framework is applicable in the subtropics as well. You wouldn't want to carry it through to the equator, of course, but in regions of the subtropics, it does seem to be useful. And it's a little unclear as to why that is, but it might be because during these extreme events, there are intrusions of jet stream, mid-latitude-like dynamics into the subtropics that make things mid-latitude-like and conspire to make QG omega quite accurate. Okay, so we're going to run with that and apply this QG omega framework within a high-resolution regional model. And so the model setup that we have here is that we have this cloud-resolving model, System for Atmospheric Modeling, SAM. Okay, and we're going to apply output from the CANESM2 large ensemble and drive this high-resolution regional model with those data, using daily 6-hourly for most of the fields, but daily surface temperature as well. And we're nudging the vertical profiles of moisture and humidity to the profiles of the GCM. And as opposed to many downscaling experiments that have been done in the past, we're including this additional process where we parameterize the large-scale circulation in terms of its length scale. And that allows you to simulate some of the effects of coupling between the vertical velocity on the convective scale and the vertical velocity on the hydrostatic scale. Okay, and that turns out to have a large effect on the extreme precipitation intensity as well. You get about double the amount of precipitation by including that coupling effect. Okay, so the domain of the CRM is approximately corresponding to the domain of the size of a single GCM grid box, so 128 by 128 kilometers with 2-kilometer resolution. Okay. And these forcings, I should add as well, are not being applied in your typical lateral boundary condition as well. In your lateral boundary condition way, they're being applied uniformly across the CRM domain. So again, one of the advantages to taking this approach is that you can change one of these inputs, leaving everything else fixed, and then ask the question of what effect does that have? So we have our 3 study locations where we've done these experiments. And again, they're focused on the subtropical Atlantic, where these dynamical contributions are especially strong. And here I'm showing a figure, which is a variant of the figure I showed before, which is just showing the dynamical contribution to the vertical moisture transport. And again, you see that correspondence. Okay. Much of what I'll focus on hereafter is just the subtropical South Atlantic, because we were able to get our largest sample size in the subtropical South Atlantic. And a lot of the results were not sensitive to, all the key results were not sensitive to the precise choice of study location. So I'll just focus on those results from the South Atlantic. And our sample size was 10, which is not equal to the ensemble size of 50 ensemble members in CANESM2. But we were able to pre-filter which ensemble members we used based on just choosing those ensemble members that were already producing decreases in extreme precipitation. There was no need to choose ensemble members that showed an increase in extreme precipitation because we knew that the ensemble average was already showing a decrease. Okay, so we could kind of pre-filter on our ensemble members that way. And furthermore, there were some ensemble members that just had too much numerical instability and they crashed. So we ended up with an ensemble size that was a bit lower than that of the original CANESM2 ensemble. Okay. So if you do some initial comparison between the GCM and the CRM, right, that's being shown here, where we go from about a week before the day of extreme precipitation until about a week after. Right, and we're showing the extreme precipitation intensity from the GCM in blue, right, the global climate model, CANESM2, and then from the CRM experiments in red. Right, and then the top panel is showing the historical period, and the bottom panel is showing the future period. So the CRM is producing about twice the amount of precipitation as the global climate model. Okay. One could argue that the global climate model is unrealistically low in terms of the amount of extreme precipitation, so that shouldn't necessarily be bothersome. All right. And more importantly, the CRM is showing that in the future period, there's a decrease in the extreme precipitation intensity compared to the historical period. So qualitatively, the CRM is reproducing that decrease, that projected decrease in the extreme precipitation intensity. So this provides some encouragement that the CRM will be illuminating for investigating these mechanisms. All right, and then you can push ahead with the controlled experiments. All right, so here in each panel, the blue is showing the extreme precipitation intensity composited over all 10 ensemble members during the historical period. The red is showing the composite from the future period. Okay, and so the red and the blue are the same in each panel. But then what changes in each panel is the yellow. So the yellow in each panel is just asking the question, well, if you kept everything the same as the historical period, but changed just one or two things, what would the effect be? Okay, so in the top panel, we're keeping everything the same as the historical period, but only changing the eddy length. Okay, and if we only change the eddy length, we see that there's actually an increase in the extreme precipitation intensity. Okay. So eddy length increase does not seem, at least as far as these simulations suggest, to be a reason for the projected decrease in extreme precipitation intensity. So maybe my earlier studies were indeed wrong in that regard. But then if you go to the middle panel and assess, well, what would be the effect of changing just the vertical stability and the sea surface temperature? What would the effect be? It's very hard to change just the vertical stability because then you get a discontinuity at the surface. So typically you would have to change both the vertical stability and the SST, the sea surface temperature, for the model to be well behaved. And if you do that, you also get an increase in the extreme precipitation intensity. So the earlier studies that were suggesting vertical stability playing a key role in those decreases, this is shedding doubt on that as well. But then if you just change the horizontal advection, so your horizontal temperature advection, differential vorticity advection, and your moisture advection, which is also part of the system. It's not part of the QG omega system, QG omega equation, but it's part of the overall physical system. If you change all three of those advections, what you see is that there is a decrease in extreme precipitation intensity. And it's actually much greater than what you would get just from changing all of the forcing. So there's some indication of cancellation between these effects, that the horizontal advections are driving a substantial decrease in the extreme precipitation intensity that's offset by these other effects. You wouldn't expect these things to add up linearly because we're not just fiddling with terms in the equation that have linear effects, but qualitatively you are seeing some of this cancellation. You can peel the onion some more and then ask the question, well, which of these advections, if you were to just change one of the advections at a time, which would drive a decrease? And changing moisture advection does not on its own drive a decrease in extreme precipitation. Changing temperature advection drives some decrease, but not as big as what you get from the CRM. It's really when you change the differential vorticity advection that you see this very strong decrease in the extreme precipitation intensity. Okay. And we've dug further. When you look at the differential vorticity advection, it's a function of the advecting winds as well as the geopotential. If you were to just change the advecting winds without changing anything else, you would not see this decrease. So that indicates that the local changes in geopotential height, curvature, are really crucial for capturing this projected decrease. Okay. I'm just going to check the time here. Okay, so I'm coming up toward 10 minutes to the hour, so we'll probably want to start questions soon. So we've sliced this a few different ways, where we've also looked at vertical profiles of omega, which indicate that there's projected decreases of omega over the entire vertical column. It's not just localized to one part of the column. Okay, and then we wanted to wrap our heads a bit around why might we expect there to be a reduction in differential cyclonic vorticity advection with warming? And for this, we can go back to the schematic that we brought up earlier in order to understand differential vorticity advection. Okay, with this decrease in layer thickness as cyclonic vorticity advection is brought in at higher levels. And then you can envision what is happening with warming, right? So think of these black curves as indicating the historical period. And then if you were to introduce warming into the system, then you might get something like the red curves here. Okay, because what you would expect with warming under hydrostatic balance is that your layer thicknesses would have to increase. Okay, and for a localized anomaly, the only way you can get a layer to thicken is if the curvature decreases at upper levels compared to lower levels. Okay, and if that curvature is decreasing at upper levels compared to lower levels, that would also indicate that the advection of cyclonic vorticity at upper levels would have to go down relative to the advection at lower levels. So that would indicate a weakening of differential cyclonic vorticity advection. So that's kind of the hypothesis we have here as to why you might expect a reduction in differential cyclonic vorticity advection. And we still have additional analysis to do there to assess whether that's actually what's happening in the models. Okay. We've also done experiments using single column models that parameterize convection and done the same sorts of controlled experiments that we were doing with the CRM. And interestingly enough, we found that basically everything we changed in the model, whether it was eddy length, vertical stability, or horizontal advection, those all produced decreases in extreme precipitation intensity. So that might also shed light on why we were coming to different conclusions from the GCM analysis, because there does appear to be sensitivity to convective parameterization. For a convection parameterizing model, all these things appear to be driving decreases in extreme precipitation intensity. So maybe we were all correct in our earlier studies regarding the GCMs. Okay, so these are basically our steps along in this long journey toward building confidence in regional projections of extreme precipitation intensity. We still have a lot of work. There's a lot of work we've done to understand the vertical velocity changes in the models, and there's still a lot of work remaining to understand that further over land regions, especially. Okay, and then comparing against available observations, and then there's satellite campaigns that are expected to occur soon that will give us even more data regarding vertical velocities as well. So that would provide continuing opportunities for validating models and building confidence there as well. Okay, so I will leave it at that and turn it back to Amir. I'm happy to take any questions, and any of you who want to dig further into these papers, I provided the references here, and you can also go to my website. Thank you very much.
So questions for Neil? Unmute your mic before you speak. Who was asking any questions?
Well, just one quick question. It's Peter Taylor.
Hi, Peter.
Okay, hi. I guess in the extreme precipitation over Spain recently, the blame has been attributed to increased temperatures in the Mediterranean. And you mentioned a little bit about sea surface temperature, and I wasn't quite sure how you were modifying that in some of your simulations.
Yeah, so the simulations we were running were prescribing sea surface temperature. Okay.
Okay, but you're talking about changes in sea surface temperature. What sort of level? 1 or 2 degrees, or?
In these latitudes, we're typically looking at toward the end of the RCP 8.5 period of around 2 degrees. Yeah.
Yeah. Okay. And the main impact is increasing the amount of water vapor in the layer above the surface, or is it in terms of changing the local convective mixing?
So that part we would have to assess further. As far as we have a pretty decent sense of the, that does seem to be the initial indication that the sea surface temperature effect is mainly due to increasing Q star, the saturation mixing ratio. Yeah, and along with that, you would expect changes in the vertical profile of temperature and moisture, so as to increase the convective available potential energy.
Yeah. Okay, thanks.
Yeah, so and in these ocean regions, I think that one thing to bring up with someone like Peter as well is you don't really have much of a boundary layer. And so the effect of boundary layer mixing isn't so strong here, but we are seeing indications, at least preliminary indications, when we perform simulations over land, that the boundary layer mixing plays quite a big role.
Okay.
Another question that I have is, you picked the South Atlantic where your signal was very strong, and you showed some analysis of that. But over land, mid-latitude land such as North America and also over Europe, even though the signal was weak, this is where people are living. And are the terms too small to do any meaningful analysis in that area?
The terms are small enough that we were cautious about doing our first analysis in those regions. But over the long term, I think that they're strong enough. Like if you were to look at the dynamical contribution over Europe from these simulations, it is still a negative contribution to the precipitation. And it is significant. So at some point, we do want to dig into that. And furthermore, I would emphasize that these are global climate models. When you look at regional simulations at much higher resolution, we're seeing pockets where the dynamical contribution is much stronger than this. A lot of that might be noise, but we still have to dig further to see if, there might be some robust dynamical effects at finer spatial scales when you deal with regional simulations. So it is still worthwhile to examine these dynamical effects to shed light on what might be happening in other land regions.
Okay, any other question for Neil? Well, I guess we don't have any more questions, so I'd just like to thank you very much, Neil, for a very enlightening webinar. We're all, of course, interested in extreme precipitation, floods and droughts. We keep hearing news such as recently in Spain, for example. You probably heard about that, but also in our own continent, North America, for example, a lot of flooding and drought recently in northeastern US, leading to forest fire and so on. So implications are very strong, and insight that you provided will be helpful in understanding why these things are happening. So thank you very much.
Thank you, Amir, and thank you everyone for coming.